Right now, 15 routers you've never heard of are deciding whether your YouTube video loads in 20 milliseconds or 4 seconds. How does a packet fired from your phone know which of 900,000 possible paths to take? Every tap on a YouTube link triggers a journey across the most complex logistics network ever built. Your phone doesn't have a direct line to Google's servers. Instead, it broadcasts a request into a mesh of 75,000 autonomous networks, each run by different organizations with different routing policies, and somehow, within milliseconds, that request finds exactly the right server in exactly the right data center to serve your video. The system is called packet switching, and it's the reason the internet works at all. Without it, you need a dedicated physical wire from your phone to every website you visit. With it, a single fiber cable can carry 400 terabits per second by chopping every message into fragments and routing each one independently. But that creates a problem. How does each fragment know where to go? The moment you tap that YouTube link, your phone's operating system breaks the request into action. First, it needs to translate youtube.com into an IP address, a numerical label like 142.250.185.78. Your phone doesn't know this address, so it sends a DNS query to a recursive resolver, usually run by your ISP or a service like Cloudflare. The resolver checks its cache. If it recently looked up youtube.com, it returns the cached IP instantly. If not, it starts a hunt through the DNS hierarchy. It queries a root name server. There are 13 root server clusters worldwide, labeled A through M, which redirects it to a .com name server. That server redirects to Google's authoritative name server, which finally returns the IP. The entire round trip typically takes 10 to 40 milliseconds. Now your phone knows where to send the request. Next, your phone constructs the actual HTTP request, get/watch, v equals DQW 4W9WGXCQ. But it can't send raw text over the internet. It wraps the request in layers, like nesting dolls. First comes TCP, Transmission Control Protocol, which splits the request into segments, assigns each a sequence number, and adds error-checking codes. Then comes IP, Internet Protocol, which wraps each TCP segment in a packet containing the source IP, your phone, and destination IP, YouTube server. Finally, your phone's Wi-Fi or cellular radio wraps the packet in a data link frame with MAC addresses for the immediate next hop. This whole process is called encapsulation, and it happens in microseconds. The packet is now ready to travel. Your phone transmits the packet to the nearest router, probably your home Wi-Fi access point or a cellular tower. That router examines the destination IP and consults its routing table, a database listing IP address ranges, and the next hop toward each range. Your home router has maybe 10 entries. It sees that 142.250.185.78 isn't on your local network, so it forwards the packet to your ISP's gateway router. That router has a much bigger table, thousands of entries, and it forwards the packet deeper into the ISP's network, toward a border router that connects to the broader internet. At each hop, the packet's time to live counter decrements by 1. If it hits 0, the packet is discarded to prevent infinite routing loops. Most packets reach their destination in 8 to 20 hops. Now comes the truly impressive part. Your ISP's border router uses a protocol called BGP, Border Gateway Protocol, to decide where to send the packet next. BGP is the postal service of the internet. Every autonomous system, a network under single administrative control, like Comcast or Google or MIT, announces which IP address ranges it owns or can reach. These announcements propagate across the internet, and routers build massive tables mapping IP ranges to paths. A typical border router in 2026 holds roughly 950,000 BGP routes. When your packet arrives, the router performs a longest prefix match. It finds the most specific route that covers 142.250.185.78. Google announces 142.250.0.0/15, so the router forwards the packet toward Google's network. The path it chooses depends on BGP policy. Some ISPs prefer routes with fewer hops, others prefer routes through certain peers, and some routes are filtered entirely for political or security reasons. Your packet likely crosses several networks to reach Google. It might go from your ISP to a regional carrier, then to a Tier 1 backbone provider like Level 3 or Telia, then to Google's network via a peering connection. These connections physically exist in buildings called Internet Exchange Points, IXPs, where dozens or hundreds of networks plug into the same switch fabric. DCX in Frankfurt, the world's largest IXP, handles over 12 terabits per second at peak. If your ISP and Google don't peer directly, the packet traverses the global backbone. Subsea fiber cables like Maria, which spans 6,600 kilometers across the Atlantic with 200 fiber pairs carrying up to 200 terabits per second combined. The packet travels at roughly two-thirds the speed of light in fiber, covering 8,000 miles in about 65 milliseconds. Once the packet enters Google's network, it hits a load balancer, a specialized router that distributes incoming requests across thousands of servers. Google operates roughly 36 data centers worldwide, each housing tens of thousands of machines. The load balancer checks the requested video ID and routes your packet to a server that either has the video cached in RAM or can fetch it from nearby storage in milliseconds. YouTube uses a content delivery network architecture. Popular videos are replicated to edge caches near major cities, so your packet probably doesn't travel all the way to Google's central data centers in Oregon or Iowa. Instead, it might land at a regional cache 50 miles from your home. The server processes your request, locates the video file, and begins constructing a response. That response undergoes the same encapsulation process in reverse. Application data wrapped in TCP, then IP, then data link frames. The return journey follows the same routers, but might take a different path if BGP routes have changed in the meantime. When routing works, it's invisible. When it fails, entire regions lose internet access. In 2008, Pakistan Telecom tried to block YouTube domestically by announcing a false BGP route for YouTube's IP space. The announcement leaked to the global internet, and for 2 hours, YouTube traffic worldwide was routed into Pakistan's network, which couldn't handle the load. YouTube went dark. This is called BGP hijacking, and it happens dozens of times per year, sometimes by accident, sometimes maliciously. There's no central authority verifying BGP announcements, so any network can claim to own any IP range. RPKI, Resource Public Key Infrastructure, is a cryptographic system designed to authenticate route announcements. But as of 2026, only about 55% of routers validate RPKI signatures. The Internet's resilience depends on redundancy, multiple physical paths, multiple ISPs, multiple subsea cables. When Tonga's only subsea cable was severed by a volcanic eruption in 2022, the island lost internet for 5 weeks because there was no alternate route. Routing also determines latency. High-frequency trading firms pay millions to shave microseconds off their routes between New York and Chicago by laying straighter fiber paths and optimizing router configurations. Gamers suffer when their ISP's peering agreements route traffic on inefficient paths. Your packet to a game server 100 miles away might detour through another state, if that's the cheapest BGP path. And routing is a choke point for censorship. Countries like China and Iran use BGP filters to block entire IP ranges and deep packet inspection to drop traffic containing forbidden keywords. The protocols that route your packets were designed for a cooperative academic network in the 1970s and 1980s, not for an adversarial global internet carrying geopolitical tensions and trillion-dollar economies. That they still work at all is a mix of engineering elegance and duct tape pragmatism. So that's the journey. DNS lookup, TCP encapsulation, ISP routing, BGP path selection, backbone transit, load balancing, and the return trip, all in 20 to 200 milliseconds depending on where you are and where the server is. 15 routers, 3 protocols, and one 50-year-old design that somehow still scales to 5 billion users. If you want more engineering deep dives like this, subscribe. Next time we'll explain how your phone actually talks to a cell tower.